Alright, in this video, I want to try and give a little bit of meaning to some of the concepts that are discussed in the textbook. The textbook does a great job of discussing the mechanics or the procedures involved in taking derivatives in higher dimensions and what that and what the result of that is, but really it doesn't give a very good job of explaining what we mean by the derivative in higher dimensions. So I want to just talk about that briefly. So we have, first of all, the first thing to note is that this chapter of the textbook doesn't make any mention of it. The textbook is really only working on functions of this type. Okay, so functions that take as an input, that take in a scalar and output a vector. Okay, and remember we called these vector functions. So just from looking at this, since we have here this function is a scalar function, this function y of t is a scalar function, this function z of t is a scalar function, we have three functions z of t, it sort of makes sense that the derivative of this function would just be the vector that's found by taking the derivative of each of the component functions. And since we know how to take the derivative of scalar functions, this sort of computationally makes perfect sense. So there's nothing really strange about that. But the question is, what does it all mean? So let's just take a second to think about that. Okay, so if you think back to your single variable calculus, we had a function, a curve, something like that, and we wanted to draw a tangent line to it, and maybe the tangent line, it looks like something like this, and it's tangent at this particular point, and so we wanted to find the tangent line. All right, and the derivative, let's call this f of x, say, right? Then the derivative f prime of x was the slope at x. So if this is x, then the slope at x is what we found as the derivative. But now, what if instead of f of x, we have a function, a parametrically defined function? What if we parametrically define this as g of t, right? Then what is this? What is g prime of t? All right. Well, because the slope at x, well, at t, where is t? T is just a parameter, right? T tells us sort of how far along the curve we are. So here's, t, and t sort of goes along like this. So what does it mean to, what's the slope at t is not really what we're talking about anymore. But if we focus less on this idea of slope, right, and more on this idea of tangent line, I think we'll have a better understanding of what's going on. And the reason that we don't want to focus so much on slope anymore is because slope is sort of, by definition, a two-dimensional or a Cartesian sort of thing. What is the slope? The slope is the change in y over the change in x. Well, if we change in y over change in x. If we try to think about what the change in y over change in x is in a three-dimensional curve, here's a curve through three-dimensional space, which could easily be defined as, if we call this, f of t, it's got components in all directions. If I think about drawing a tangent line at this point on the curve right there, then maybe my tangent line looks something. My tangent line looks like something like this, and it's sort of going through space. And if I said, what's the change in y over the change in x for this line, that doesn't make any sense. Okay, well, why doesn't it make any sense? Well, because what about z? We haven't thought about the change in z. So maybe we should just do the change in y over the change in x over the change in z. No, I'm just kidding. That is equally doesn't make any sense. But we can still clearly draw this tangent line, and it's not hard to visualize what it means to be tangent. We have to talk about the properties of it in a little bit more detail, but we can have this tangent line. So what we really want to know is we don't care about the slope. Slope is just something, is the name we gave to it in two dimensions. But what we really care about is we care about the direction. So the direction of this tangent line. And we can specify the direction of tangent lines with vectors. So a vector, the derivative of a parametrically defined curve in space is really just a vector which is tangent to the curve. So it's a vector which is tangent to the curve. So let's take an example here real quick and work this out so we can see. Let's take a look at the function f of t is equal to 3 cosine of t I hat plus 4 sine of t j hat. Okay. And we have a picture of that, which looks something like this. Okay. There's my parametric curve. Let's take the derivative of this. Easy enough. Let's move this over here. F prime of t is just the derivative of each of the components. So derivative of cosine is negative sine, so we end up with negative 3 sine of t, and then plus 4 cosine of t j hat. Okay, great. So let's pick a point and see exactly what this vector, because remember this is a vector. This is allegedly this is the tangent vector. Let's take a look at a specific point and see what's going on. So I'm going to arbitrarily pick t is equal to pi over 6. Okay, so f of pi over 6, we need to first find where the point is on the curve. F of pi over 6 is cosine of pi over 6 is root 3 over 2. So we have 3 times root 3 over 2 I hat. And then sine of pi over 6 is 1/2. So we have 4 times a half, which is just 2 j hat. Okay. And then f prime, let's find that. F prime of pi over 6 is negative 3 times a half, which is negative 3 halves I hat. And then cosine of pi over 6 is root 3 over 2, so this is going to be 2 root 3 j hat. Okay, so there I have my function value at pi over 6, and I have the derivative at pi over 6. So let's go ahead and see what those vectors are. So, okay, so 3 root 3 over 2. So this one, the coordinates of this are about 2.6 is 3 root 3 and then 2. And then the coordinates of this one, well, negative 3 halves is negative 1.5. And 2 root 3 is about 3.5. Okay, so let's take my first vector, 2.6 comma 2. That one's going to look like, so here's 2.5. So 2.6, and then I go up to 2, and you can see that that's right there on the curve. So this is my vector. The vector is 2.6 comma 2, and t is equal to pi over 6. Okay, now what's this negative 3 halves 2 root 3? Well, negative 3 halves 2 root 3. The vector is in the x-coordinate, I go negative 1.5, which is right there, and then up 3.5. So there's 3.5, just like that. Okay, so did I get that about right? Looks like it. Okay, so now if I take this vector, that vector does not look terribly tangent, but if I take this vector and I slide it out here, we can see that the vector given by the derivative, the vector right here given by the derivative, if I translate it out to the point, we see that it is a tangent vector at the point. Okay, so what does this tangent vector tell us? Well, one, it tells us the direction that is tangent to the curve. And if we actually found the slope of this vector, the slope here, just the slope of this vector is the slope of this vector is 3.5 over negative 1.5 approximately. All right, and that's going to be approximately equal to the value if I made an equation for this ellipse in terms of x and y, which would be easy enough. It would be x squared over 9 plus y squared over 16 is equal to 1. And then the derivative of this parametrically will be 2x over 9, and then the derivative of y, which is going to be 2y y prime over 16 is equal to 0. So we get that if we solve this, so we get that 2y, well, let's just get y prime over 8 is equal to negative 2x over 9. So we get that y prime is equal to negative 16x over 9y. Okay, and if I plug in my x coordinate was 2.6, so at this particular point is negative 16 times 2.6 over 9 times 2, and this is approximately negative 2.3. All right, if I do up here 3.5 over negative 1.5, this is also approximately negative 2.3. So we get the same answer no matter how we think about it. Okay, but the important thing is that we have a vector whose direction tells us the direction of the tangent line. So in the next video, we'll examine what the length of this vector means. We know what the direction is, but next one we'll check out what the length means. Okay, great.